So today I'm going to be talking about recursive language models inside of DSPy. So these are a new module inside of DSPy called DSPy RLM. Just a little bit of context about me is that I'm a core contributor to DSPy and a co-founder of Cmpnd. So language models are obviously smart. I'm sure we all use them all the time, but when you try and put too much context into them, they really suffer. And you see this, people are constantly trying to improve the context lengths of their models, right? Anthropic just yesterday, the day before, releasing their 1 million token context opus, right? This is a problem that everyone is kind of lasered in on right now, is that when you want to scale up and put more context into your model, the performance degrades. And so the team at Chroma put together an awesome report, I'm standing for the slide, put together an awesome report about context rot, which is basically the thing that happens when you put too much into your model. And so this kind of comes in three different task definitions for what can go wrong. Is that the first is you want to do needle in a haystack. And so when you want to do needle in a haystack and you need to find one specific thing inside of your prompt, then and there's a lot of context, you need whatever model you're using to actually find the specific thing. Finding the specific thing, really hard. The second thing is when you have a lot of context that you need to attend to all of, right? If you are writing a book summary, you need to kind of attend to everything because all of it is important to the global context. And the third is when you need to output a lot of tokens at once. In this case, this task is repeated tokens where there's no reasoning required. The task is repeat the input verbatim. That's it. And you see that kind of this came out a little while ago, but even like Claude Sonnet 4 falls off of just repeating tokens, right? And so this is like a pitifully easy task that we still don't have solved. And so that's kind of the motivation to lead us to RLMs, is that RLMs are a general inference time strategy for improving the ability of language models to reason across long contexts. And so the key insight here is that we actually want to take what a user says and add that as the part of the environment. So if you have a book that you are trying to work with in some way, you want to summarize it, the language model should be able to do things to that book. It shouldn't have the entirety of the book in its context. And so how do we actually do this? Is that we let the models write code. The models are really good at writing code. And so what we do is we put it in an environment where it can write variables, it can write functions and reuse them in order to actually build up whatever it needs to do over time and delegate out to other language models so that it doesn't need to deal with them all at once. To make that more concrete, if you want to summarize all the chapters of a book, it's a lot easier to summarize each chapter individually than to write 12 summaries in a row. And so RLMs let you deal with context rot. So what you do is you have everything in a variable, and so the LLM isn't actually seeing the entire book at once. Maybe it's seeing a list of strings that represent all the chapters, and it'll actually just write a function that calls out to a sub-language model and says, hey, summarize this whole string. And this allows you to actually avoid some of the degradation that comes with having really long contexts. The second is that you can actually handle pretty much infinite context lengths. Of course, this has limitations, but really what you can do is you can let the model explore the actual form of whatever your data is. Maybe you don't even know that the book has chapters. You just know it's one giant string. You can just throw that at the model and see what it does. The third thing is that when you need to actually reason across the whole context, RLMs allow you to do this. Is that you can split up your context into parts and deal with it one at a time. And then lastly is that it actually turns a lot of your long context problem into code and reasoning problems. And this is really important because models are really bad at long context problems and really good at code and reasoning problems. And so this is a fundamental way in which it changes how the model interacts with your task and allows it to do new, exciting things. So one of the most common questions that we get asked is Claude Code an RLM? And the answer, it can be. By default, the important thing about an RLM, there's three important things. The first is that the prompt is actually saved to some kind of symbolic object. This could be a file, it could be a variable. The RLM needs to interact with the actual prompt itself without needing to see all of the tokens of that prompt in its context window. The second thing is that the model needs to be able to interact with it by actually writing code. This is really important, is that if you are parsing a book, if you aren't writing code, there's no way to do that without having the entire book in your context window. And this is what we really want to avoid. And the third thing is that we want to give the language model or the RLM access to call itself inside of your code environment. And what this allows you to do is it allows you to delegate out functions to subcalls. And you might be thinking, is this a sub-agent? Kind of. It's a form of a sub-agent where you're delegating out a specific task, but you're integrating the results into code. Is that if you summarize all n chapters of a book, you'll just get a Python list back. That's the list of chapters. That's what you want. This is a way to program with the actual context. And so now we arrive at RLMs in DSPy. So if you look at kind of the hello world of what you would do in the normal RLM, and so this is the library created by Alex Zhang, one of Omar's PhD students at MIT. He was the author of RLMs, and he created an RLM library. And so you can see it's pretty self-explanatory. You call .completion on your RLM, you pass it whatever context, and you get a response out. Now, importantly, you don't really know anything about the response, and that's by design. You are passing in a string, you're getting out a string. For those of you that think in DSPy signatures like I do, this looks like a string to string signature. Is that if you wanted to write an RLM in DSPy, what you would do is you would have context to response string. You can wrap the RLM module around that signature, and then you can call it with a context string. Now, where this gets really interesting is that most DSPy tasks do not look like context to response. In fact, you really should be writing DSPy tasks where you know more about the actual problem that you're solving. You probably know something about the structure of your task. And it could be the types, it could be the actual task you want the RLM to complete, it could be the inputs, outputs, there's a lot of things. So for those of you that aren't familiar with a DSPy signature, there's three main parts. The first is the task at the top. These are the instructions of what you want the language model to actually do. In this case, you write it as a doc string to the class. So for this example, what we're doing is we're extracting emails, and that's what we're telling the model to do. For the inputs, we have three different inputs, and we know the types. Subject is a string, thread is a string, and attachments, that's a dictionary with stuff inside it. We don't know the exact lengths. We don't know how long everything is, but the inputs are there, and we can kind of give those to the language model as separate inputs. And I'll explain that in a second. The last thing is the outputs. Is that for the outputs, we just want this to be structured outputs. It's pretty common to use structured outputs these days because they're really wonderful. And so we want a pydantic object acquisition event, and then we also want a dictionary. And importantly for this dictionary, we want a specific literal out of the second part, is that we want it to map from to-do names to actual priority literals. And so kind of what DSPy does is that if you have that signature, what you can do is you can give that to an RLM, and it will then be able to take on the structure of that signature. And so you have your inputs in that example, which are your subject, thread, and attachments, and those are all separate variables that are laid out for the RLM. You have your outputs, which are a format, which are the two objects that we described. The RLM needs to submit objects in that format. That's the thing, is that we still maintain structured outputs, even though the actual outputs we want aren't coming from the language model. And then the third thing is that we can actually use this the same as any other DSPy program. So I've been talking for a second, and now I'll give you an actual demo, which is that a few weeks ago, there was a flood of state-of-the-art solutions to ArcAGI 2. One of those was Agentica, who got what was at the time state-of-the-art with 85.28%. And they used a deeply recursive RLM to actually do this. And so I went ahead and recreated an ArcAGI2 solution, or program, not solution, in DSPy. And I think that'll really help illustrate what's going on here. So for this demonstration, I'll be comparing the actual DSPy vanilla, the DSPy RLM to the vanilla RLM. So we see that of this subset of 15 tasks, DSPy does slightly better, but I don't think that's what you should pay attention to here. I think what you should pay attention to is the actual iterations that it takes in order for DSPy to both succeed and fail. Is that because we know what your program looks like, we can know that we can go faster. Or the language model doesn't need to explore all the context every time. So here's the first thing, is that when you write a signature, when we write this signature, we are telling the RLM that the inputs are going to be of type a list of ints. The RLM knows that, and it can interact with it like a list of ints. It doesn't actually need to explore or figure this out. And so you can see how it gets off to a faster start really easily in this example. So we start over here. You see that the first thing it does is that it knows that this is a list. So it's actually a list of dictionaries for this one. Is that it knows that this is a list, and so it grabs the first example. It doesn't need to query into it first, check the format. It can just start. And then it grabs the input and output, which it gets told are the keys up above, and it can just go. And now an RLM, it has the exact same information. It's the same prompt, but it still has to explore the context. It doesn't have these typed variables in its context. And so having the typed variables is really important here. Now, the second part that's really important is structured outputs. Is that when you use the RLM, it is not able to submit a response unless that response actually matches whatever the output type of your signature is. In this case, our output type is a list of ints. Gotta say it again. And so if the RLM tries to submit something that isn't of this data type, it will just return to the RLM and say, hey, this was an incorrect type, you need to restart. And the vanilla RLM implementation, it can't do this because it doesn't know anything about the types of your outputs. And so you can see here what the vanilla RLM implementation asks it to do is just submit things into this final function, and then you hope. And that's really not what we want here. You want to use these to do some task. In this case, we want to get list of ints out, and so we will force the RLM to give us that out. And you can see this comes through, especially with the DSPy version, we don't have any parsing failures because if the RLM submits something wrong, we force it to try again. Whereas the vanilla one, it doesn't actually fit our format 100% of the time. And the last thing is that you can provide the RLM tools in its context that it can call just like normal Python functions. And so in this case, we give it a verification function, which is just a nice helper to run it against the input examples. It doesn't give it any advanced information that it otherwise has. It's just a pre-written function that runs whatever its solution to ArcAGI is for that problem against the examples that has been passed in. And we can just save it this effort. And so that's the whole point here, is that because we know the structure of our task, we can write a signature around it and help the RLM do better on our task. And this comes through in the actual iterations that it takes to solve. Is that the DSPy version takes 7 on average, and the vanilla version takes 15. And this is just because we know more about this task. And so here, this is kind of a messy chart, but really you can see that the DSPy version is generally a lot more condensed, right? Is that you have fewer blue steps at the beginning. If you kind of check any one of these problems, except for that one, most of them have fewer exploration steps than the actual vanilla version, right? Because we know about our problem. And so now I think we're just going to go a little bit into the actual trajectory of one of these. So this is the training example. The task is just to extract out whatever the shape is. And the outputs here are different shaped arrays. They're not all the same shape. And so I already have these cached. And actually both the vanilla RLM and the DSPy RLM end up solving this question. My point is not that the DSPy one is universally better. My point is that we can provide structure that helps it start iterating faster. So in the DSPy RLM case, you see that from the first iteration, it's already talking about the input grids, and it's starting to actually investigate what the examples themselves are. And then we come down here, and so it sees all of the input and output shapes. And by number 2, it's already trying to analyze examples, and then down here by iteration 4, it actually starts to try things. And this is generally faster than the vanilla RLM can do. Because the vanilla RLM, if you look at this first call up here, is that it has to start off by printing out this context. It doesn't have a choice. It doesn't know anything about the task that it's completing. We provide a user prompt, but it just doesn't know. So now that you've seen an example of kind of what a DSPy flavored RLM can do, one of the benefits you get out of the box from using the DSPy version is that you can just optimize it. If you've looked at the internals of the React module, it looks very similar. It calls itself in a loop, and then it extracts itself at the end. It's that simple. And so you can optimize these prompts like any other DSPy program, and that's really awesome. And that really brings me to the core promise of DSPy, which is that there's going to be new modules. There's going to be new prompt optimizers. And I don't know what these are, but the thing is that you can keep using your signatures because the tasks that you need to solve will stay the same. And we're seeing some validation around RLMs in the industry. Is that Anthropic published their programmatic tool calling specification, where they measure their model's ability to do a lot of the same benchmarks that the original RLM paper was doing. What this is really saying is that what they do is the exact same flow as an RLM. They take their context, they send it to their API, Claude writes code, it comes back, they execute the code. If there's any functions in it, they execute the functions, passes it back to the code execution, passes it back to Claude, and finally Claude passes it back to the user. And so the place that they're using this is, one of them is in Claude for Excel, where it's really, really inefficient to have a language model manually writing out the values of Excel cells. That sucks. And so what they can do is they can use their programmatic API to change a bunch of cells at once. Is that if they want to edit 20 cells with a normal tool calling agent, this requires 20 tool calls. And that is not efficient at all. Is that if this is a program, it can do 20 tool calls in the same pass. And so it's much more efficient. And they cite a lot of the same improvements that we see people who write things with DSPy see, which is they see improvements in cost, improvements in accuracy, or improvements in latency. In this Anthropic engineering blog, they see all 3. So now I'm just going to go quickly into some different use cases that we can see here. The first is needle in a haystack. This is, again, when you have some small bit of information that you want to parse out. It could be looking at logs for anomalies. It could be trying to find some signal in just a large data set of any user conversations. The second is long context QA, particularly code-based QA is really interesting here. We see that kind of RLMs can attend to much longer context and explore a lot more areas and are able to actually do better on answering some code QA questions. The third is multi-hop reasoning, where you have a large retrieval data set and you want to answer questions that require context from multiple documents. The fourth is clustering, and this is one I'm really, really personally excited about, is that you can actually look at a data set and find the trends in it. And so, for instance, one of them could be trace analysis. It could be user sentiment analysis. It could be user intent. There's so many things you can do here because you can attend to all of the giant context, right? You can't put all of your traces into a normal language model. And the last is symbolic manipulation, which is what we see with ArcAGI. It's where you can actually take whatever inputs you have and run experiments and try things and validate them through code and then submit the result. So just very briefly, for the needle in a haystack, one of the DSPy users and contributors, Raymond, he wrote an implementation for DSPy for longbound eval. And basically in a day of hacking on it, he was able to get a top 5 score. And so this is just really exciting and it's using Gemini 3 Flash, which is not the best model on this list. And so it's really exciting that kind of RLM is able to support these long context operations. The second, like I said, code-based QA. Now, I've done a lot of selling of RLMs, and I don't want to, they're not a silver bullet. There are issues. The first is that they might have higher token usage. They could be slower, right? Code takes a second to run, unless I'm using Monty. They might have slower or worse performance on less structured context, right? So if I am running it on a novel where I don't know anything and I'm passing it as a string, maybe the RLM would be slower than if I knew more about it. And the third thing, and this is something that Alex at the lab at MIT is working on, is post-training models to be better at being an RLM. Is that there's a lot of ways you can improve at managing your context, delegating to sub RLMs. And the last is different context failure modes. Is that if something gets poisoned and something goes wrong in your trajectory, this does not solve that. And that's still an open problem that I think is going to be really interesting to see the solutions to. And so I want to end off by telling you about DSPy open source, because there's a lot of great things coming down the pike, and I am hoping to see a lot of you in the GitHub issues and hear more about what you're using DSPy for. So next week, we'll be releasing DSPy 3.2. This is just a new minor version cut, which has a lot of fixes over time. And kind of beyond next week, what we're seeing is we're going to see some more RLM improvements, which means in being able to handle better pydantic types, being able to handle multimodal support, more code interpreters. There's a lot of cool things that can come here. The second is with chat history, is that using DSPy for agentic applications has been hard sometimes. And so we really want to work on improving this developer experience. And so I'm really looking forward to working with you in the community to getting feedback on how to make this the best possible experience of building chat agents. And then thirdly, a complaint we get a lot is that the documentation is not great, and we want to help remedy this. We think the documentation can be great and that DSPy can be a lot easier to learn for people. And so we're really excited to help fill in some of the API reference that's not filled out yet, and also help bring on new users. This is something we're super, super passionate about, is that we want people to come and experience DSPy and fall in love in the same way that we have. And so as you're doing this, if you have any questions or ideas or bugs, please let me know. I'm on the Discord, I'm on Twitter, I'm on GitHub, anywhere. Come find me. Thank you.